Hello and welcome to this webinar on using the Gamlen series to carry out compaction analysis. I'm Rebecca McVicker, I'm the Product Director at Gamlen Tableting, and as I said, we're going to be learning about compaction analysis today. The Gamlen series can be used for other applications. It can be used to make small batches of tablets for other tests such as dissolution, disintegration and stability testing. But today we're going to be focusing on compaction analysis. First of all, why do we want to analyse compaction? We analyse compaction to make better tablets. And what is a better tablet? A tablet that has enough mechanical strength to withstand handling and processing without showing any breakage or chipping issues, but also a tablet that's porous enough so we're not hindering dissolution. And we also want a tablet to be free of defects, such as those caused by sticking and picking. The difficulty with this combination of criteria is that they're all working against each other. A very porous tablet is not likely to be very strong, and in order to avoid defects, we need a well-lubricated blend. But an overly lubricated blend can lead to issues with tablet strength, where the particles are too well lubricated, they don't adhere to each other in the tablet, and you end up with a weak tablet. Ideally, we want to know if we are achieving all of these criteria before going into full-scale manufacture for any formulation. And this is where compaction analysis comes in. If you're not carrying out compaction analysis, it's likely that you're trying to infer compaction properties from other powder properties. There are many properties that influence how a material compacts, and these can be analysed in order to estimate powder compaction behaviour. But when we take this approach, we're only ever getting best estimates on whether a material will make a good tablet or not. Or, for example, when we're comparing different materials, we might compare them in terms of particle size, particle shape, and so on, but we're not actually interested in those differences. We're interested in the difference those material differences are going to make to the final tablet. So by instead looking at the compaction process directly and analysing that, we can make much more definitive conclusions from our analysis and get a much better idea of how our materials are going to behave during full-scale manufacture. Moving from inferring compaction behaviour to measuring it directly has several different advantages. It takes less time, the results are less complex to interpret, and you're closer to looking at the information you're actually interested in. Using other material characterization techniques can still be useful when you want to understand why, say, one batch of API has behaved better at secondary than another. So using the Gamlen, you can establish which is the better compaction behavior, and then use other material science techniques to identify why that material has behaved better. But in a lot of cases, we simply want to know if our material is going to make a good tablet or not. In that case, you can use the Gamlen by itself. For example, if you're looking at evaluating different supplies or sources of a material, then using the Gamlen, you can compare them directly in terms of their compaction behaviour and determine whether changing to an alternative source, for example, will affect your final tablet quality. Gamlen are not the only ones that are recommending that companies take this approach. The United States Pharmacopoeia published Chapter 1062 a few years ago, and the quote on screen essentially says that we've been making tablets for over 100 years, but we still have the same problems we had 100 years ago, problems with tablet failures associated with poor lubrication and poor tablet strength and so on. So Chapter 1062 is the United States Pharmacopoeia's recommendation on the kind of testing and data that companies should be generating in order to avoid these problems going forward. The testing that the United States Pharmacopoeia recommends in Chapter 1062 can be summarized by the compaction triangle. They essentially recommend measuring 3 different values: the compression pressure used to make the tablets, the solid fraction of the resulting tablets, and then breaking those tablets to measure their tensile strength. Once you have these 3 values, you now have 3 relationships: the tabletability, compressibility, and compactability. And once you have those 3 relationships, you have 3 ways of evaluating a powder or comparing different powders, different formulations, or different sources of material, or so on. When we're generating this data, it's important that we know exactly what force is being applied to the tablet so that we can accurately calculate the compression pressure, and that's where the Gamlen comes in. In order to calculate the solid fraction, the one piece of information you need before you start your compaction analysis is the true density of the material being compacted. You need that in order to calculate the solid fraction. And the solid fraction, if you're not familiar with the term, is essentially the inverse of porosity of the tablet. A tablet with a high solid fraction will have a low porosity. A solid fraction of 1 means a completely solid tablet. If you do not have the true density value available at the time of testing, you can still get beneficial information from compaction analysis. You still have the tabletability relationship available to you if you don't have the true density value at the time of testing, and that is often the most useful piece of information you get from compaction analysis, and it's the most sensitive to differences between different materials. The true density of most well-studied excipients and APIs can often be looked up. It can be measured by helium picnometry, but in the case of a blend, the value is additive, so you can calculate it based on the true density of each of the components, as long as you know the percentage of each component in the mix. But as I said, it's not essential to getting beneficial information from compaction analysis. And then the tensile fracture stress, you break the tablets in the same way as you carry out hardness testing. But this extra piece off onto the side of the triangle is just saying that we always account for the tablet dimensions. So even though we measure the breaking force, similar to a hardness tester, we convert that to tensile strength, because that it takes account of the tablet dimensions. Similarly, when we compact the tablet, we measure the compression force, but we convert this to compression pressure to take account of the tablet dimensions. By doing this, this means that we don't have to use the same tablet size and shape for compaction analysis that we're using at full-scale production. It also takes the technique away from being specific to one tablet size and shape and makes it more of a materials characterization technique. The compaction triangle covers the recommendations from USP 1062. However, it doesn't give you advice on how you should evaluate lubrication. And evaluating lubrication is, of course, essential to avoiding problems with sticking and picking in production. The way the Gamlen measures this is by measuring the forces required to remove the tablet from the die after it's been compacted. So once the compaction has occurred, at this point the tablet is now stuck to the base of the die and it's still inside the die. So the first force is the detachment force, detaching the base of the tablet from the base of the die. And then the second force is the ejection force, which is the force that pushes the tablet out of the die. And it's pretty intuitive to think that if those forces are high, then you have a poorly lubricated blend and you're likely to have problems with sticking and picking in production. The next section describes how you analyze compaction. Using the Gamlen system, full compaction analysis is carried out in 3 simple steps. First of all, you make the tablets on the Gamlen, then you measure the dimensions and mass of the tablet, and then you break the tablets using the Gamlen TTA. When you make the tablets on the Gamlen, first the compaction occurs, and then the detachment and ejection operations occur, as I mentioned, in order to evaluate lubrication and to remove the tablet from the die. Then you measure the thickness of the tablet using a micrometer and the mass on a balance. The Gamlen TTA, or tablet tensile analyzer, measures the diameter of the tablet before breaking it, similar to a regular hardness tester. In order to carry out a full analysis, we normally recommend making 15 tablets for each sample. This involves using 5 different compaction pressures and making 3 tablets at each pressure to give you a full profile. This is better for evaluating and comparing materials. A normal test with a 6mm punch and die will typically require less than 2 grams of material and can be completed in about half an hour. So you require very little material and it's fairly quick. The accessories provided by Gamlen are balance, micrometer and TTA. If you take those as part of a purchase, then our software can link up with those, so you don't have to do any data entry for those values. However, if you prefer to use your own micrometer, balance or hardness tester, we can set up the software for you for manual data entry for those values. This video demonstrates how the Gamlen can be used to generate compaction data. First of all, you add powder to the die, and then the die is tapped to level out the powder. You slide the die into the instrument so that it's directly beneath the punch, as shown, and you can see on the right the controller software that's used to control the Gamlen. You select the compaction load you want to apply to the powder and then start the compaction. You can also work or operate in fixed thickness mode, and this allows you to compact a tablet to a certain thickness as opposed to using a certain compaction load. Next, to carry out the detachment and injection steps, we rotate the die through 90 degrees, as you can see, and this allows the detachment to be carried out. The die base slides, and you can see that there's a cavity in the die base. So when the punch now comes down, it's going to push the die base and slide it. We're going to measure the force that requires, which is the detachment force, and when this operation is complete, the cavity will be underneath the tablet. Press start, the punch moves down, and you can see the base sliding to move the cavity underneath the tablet. And we measure the force that this requires. You then open the lever to allow the die to rotate back to the original position, and this allows the ejection operation to be carried out. The lever is opened, die rotates back, lock it back into place. You press start again, and now the punch moves down to eject the tablet, to push it out of the die and into that cavity in the die base. We measure this force as well, and then the detachment and ejection forces are used to evaluate how well lubricated the tablet is. You can now remove the die from the instrument, slide the base back to its original position, and there's our first tablet. That's the making tablet step. So the next step is measuring the tablets, the mass of the tablet and then the dimensions of the tablet. So using the balance we supply, or we can also supply interfaces for many Mettler Toledo and Sartorius balances, instead of having to enter the mass value into the software, you can press a button and it's captured automatically by the software. Similarly with our micrometer, where you place the tablet underneath the foot of the micrometer, using our one, if you click the thickness button in the software, it captures that value for you automatically. And finally, we're using the tablet tensile analyzer to measure the diameter of the tablet and then break the tablet to measure its hardness and then calculate from that the tensile fracture strength. And you can use a standard hardness tester for this step, but most commercial hardness testers are intended for fully formulated tablets. Ours is more sensitive at the lower hardness values. This is to allow you to test, say, an API on its own, so you can still generate useful data from that without having to only work with fully formulated samples. This is the Gamlen dashboard software. This is our analysis software package. You can see I've just clicked refresh in the software and the data for the first tablet appeared in each of the graphs. We're going to skip ahead to 14 tablets later. As I mentioned, for a standard test, we want 15 tablets, so using 5 different forces and 3 tablets at each force, and this gives a full profile. When you're finished making, measuring, and breaking the tablets, you click refresh in the software, and this automatically captures all the data you've generated and displays it in these graphs. You can see here that our software gives you these red and green zones, and this is to give you an idea of when you have good and bad compaction behavior. The red and green zones are based on the experience of our founder, Michael Gamlen, and also on the recommendations of several industry and academic tableting professionals. The top 2 graphs on the left are the lubrication evaluation graphs, the detachment and ejection stress profiles. So if you have tablets in the red zones in these graphs, then your tablets are poorly lubricated, and you would expect sticking and picking in production. The 3 tablets in the bottom, or the 3 plots in the bottom row on the left, are the compaction triangle plots, so the tabletability, compressibility, and compactability plots. The first one, the tabletability, shows you how the strength of the tablet changes with compaction pressure. And in this example, we're looking at MCC, so we've got very good tabletability behavior with all of the tablets in the green zone, and the tensile fracture strength increasing with increasing compaction pressure. The next one is the compressibility profile, and this looks at how the solid fraction of the tablet changes with compaction pressure. So, as I said, a tablet with solid fraction of 1 has no pores in it. So the red zone here is set at a solid fraction of 0.9. So if your tablets are above that point, then you have less than 10% porosity in your tablet. And this is a problem for 2 reasons. One, you are likely to have longer dissolution times as liquid can't penetrate into the tablet without the pores. And it's also associated with capping problems in production. The third graph is the compactability profile, and now we're looking at how the strength of the tablet is changing with solid fraction. This can be interesting when you have samples that have different tablet tensile fracture stress values, different strengths, but the same solid fraction values. If you, in that instance, you know that the differences in strength between those tablets are not due to differences in porosity. There's something more fundamental about the interactions between the particles that's giving you those differences in tablet strength. So that comes more into play when you're looking at formulation development. I won't go through every single graph in this set, but just to mention, we also measured the elastic recovery of the tablets. So how much the tablet increases in thickness after compaction. And high elastic recovery values have been associated with capping. It's not a definitive indicator, but there has been found to be an association. So if you're having capping issues, this can be an interesting piece of information to look at. The next section of the webinar is on the applications of this data. The first set of data is looking at how the Gamlen data can be used to predict how a material will behave at full-scale manufacture. We often get asked how the Gamlen data can be used to do this when the size and shape of the tablets made on the Gamlen won't match with that made in production, and the Gamlen compaction speed is much slower than a full-scale tablet press. Well, in this case, this was taken from a paper published by Kendall Pitt at GSK. Here he was looking at comparing data for tablets from a full-scale FET-A tablet press with data of compaction analysis data from the Gamlen. He looked at two different formula. One was a direct compression formulation and one was a wet granulation formulation. On this slide, we're looking at the data for the direct compression formulation. The Gamlen tablets were flat-faced cylindrical tablets. Gamlen tablets are always flat-faced cylindrical tablets, and 100 mg of the blend was used per tablet. At full scale on the FET-A press, the tablets were caplet shaped and they were 8 times larger with 800 mg of the powder per tablet. You can see here that the data for both the tabletability and compressibility profiles is very similar for the Gamlen and FET-A tablets, that there's really no significant difference between the two, that the data for those tablets track very well. So from this, we can see that the Gamlen predicted very well how that formulation was going to behave at full scale. The next slide is looking at the same data but for the wet granulation formulation. Again, the Gamlen tablets were flat-faced cylindrical tablets with 100 mg of the powder per tablet, and at full scale the tablets were convex shaped with 350 mg of the powder per tablet. Again, we're seeing no significant difference between the data generated on the Gamlen and the values measured for the tablets from the FET-A press. Both the tensile fracture stress and the solid fraction values are very similar between the two sets of data. So from this we can say that the Gamlen data is predictive of full-scale behaviour. We do always put in the caveat that we don't claim that it's going to be identical at all times. Sometimes in the cases where you have a material that's very speed dependent, starch is really the main example. You will see differences, but in any case we've looked at whenever people have generated Gamlen data, it's been useful in predicting what's going to happen at full scale. On this slide we're looking at how compaction analysis data can be used to assess lubricant efficacy. In this example, we're looking at 3 different excipients, lactose, ludicrous and mannitol, and in each instance, one set of tablet was made using magnesium stearate as the lubricant, and another set was made using sodium stearyl fumarate, or SSF. In this case, we're just looking at the tabletability and injection stress graphs. The tabletability are on the top row and the ejection stress profiles are on the bottom. This is because, one, to keep the data relatively concise, but also when we're looking at lubricant efficacy, these are the pieces of data we're most interested in. We want to know if the lubricant is causing any changes to the strength of the tablet, which we see in the tabletability graph, and we also want to know, is the lubricant effective, which we're seeing in the ejection stress graph. And finally, we're also just looking at these two plots because both of them are independent of the material true density value. So if you didn't have the material true density value when you were carrying out these tests, you would still be able to generate this data. That would still be available to you. So in the first example, looking at lactose, we can see that the magnesium stearate lactose tablets, which are the solid circles, these tablets are stronger than the SSF tablets across all of the compaction pressures we looked at. We can also see in the ejection stress graph that the ejection stress values are reasonably similar, so the lubrication properties are reasonably similar. The magnesium stearate is slightly better as the values are slightly lower than the SSF, but there's not much of a difference. So in this instance, if you were choosing between these two lubricants, it's likely you would go with the magnesium stearate as it's giving the stronger tablets and there isn't much difference in terms of lubricant efficacy. For the next example, Ludipress, which is a premix of several different excipients. Again, we've got magnesium stearate lubricated tablets and SSF lubricated tablets. Here, the SSF tablets are actually stronger than the magnesium stearate tablets across most of the compaction pressures we looked at. But there's an important feature in this profile, and you can see that after or above compaction pressures of 300 megapascals, the strength of the SSF tablets drops off sharply. And this is an example of overcompaction happening. I've got a slide talking about that a bit more later on, but this is a risky behavior for a material when you're going into production, particularly if you don't know a material behaves like this. Because if you're in production and you have you're using a material like this and the tablet hardness starts to trend down for any reason, often the reaction is to increase the compaction pressure to improve tablet hardness, but in this case you could be making the situation worse because you're dropping off over this edge. Looking at the ejection stress graph, we can see that the magnesium stearate is clearly the better lubricant in this example, that the SSF is actually hitting the red zone for ejection stress values. They're higher, so more poorly lubricated, more likely to stick and pick, whereas the magnesium stearate tablets are solidly in the green zone. So in this example, even though the SSF tablets are stronger than the magnesium stearate at lower compaction pressures, the safer choice would be the magnesium stearate tablets. They are in the green zone for the tabletability behavior and they're solidly in the green zone for the ejection stress. In that case, the magnesium stearate will be the better choice. And in the final example, we're looking at mannitol, again for the same two lubricants. Here, there is no discernible difference between the tabletability data or the ejection stress data. So from this data, it's still quite useful information. Now you can choose your lubricant based on any other factor. You could choose whichever one happens to be more readily available or whichever one happens to be cheaper. So for this study, if you were doing this for a real product, probably look at different percentages of lubricant and maybe look at other lubricants, maybe look at different blend times. But this is just to show you how easy it is to see the effect of these choices on tablet quality using compaction analysis data. The next set of data is looking at comparing different sources of MCC in terms of their compaction behavior. And this type of alternative supplier evaluation can be very useful for identifying other sources of material, potentially cheaper sources of the material, or just de-risking supply. So you're not single sourced on any one material. And using compaction analysis to do this, it means you can ensure that you're not compromising on tablet quality by changing to a different supplier or source. So again, we're looking at just the tabletability data and the ejection stress profile. And again, you wouldn't need to have the true density of the material to generate this data. In this instance, we're looking at 3 different sources of MCC. And let's say that we are starting out, we've been using MCC source C and we're considering using source A and B. From the developability graph, you can see that if we change from source C to source A, there's a drop in the strength of the tablets. If we change from source C to source B, there's no real significant difference in the tabletability data. The tablets are of similar strength. And here we're looking at just the MCC by itself, it's not been formulated. So this difference, considering that MCC provides a lot of the strength in a lot of tablets, that this difference could be significant if you know that your product has a history of low tablet hardness problems. If that hasn't been an issue for your product, then you may be willing to accept that change, but if you are concerned about tablet hardness, then source B would be the better option. From the ejection stress graph, you can see that by changing from source C to source A, there's a drop in the injection stress values, so they actually require less lubrication than our current source C. Whereas if we change from source C to source B, the open circles to the grey circles, we're now increasing we're seeing an increase in the ejection stress values, so that those tablets require more lubrication in order to avoid sticking and picking. So in this instance, if you're concerned about sticking and picking, if you know your product has a history of it or it's a particular worry for some reason, then you are going to want to avoid source B. You're probably going to prefer, if you need an alternative source, to go with source A. So you can see from this data again how easy it is to see the effect of your choices on compaction using this kind of data. So from this and your knowledge of your formulation, you could say that either tablet hardness is more of a concern, so we want to stick with source B, or you could say sticking and picking is more of a concern, so we want to go for source A. For the final slide, I'm going to talk a little bit more about the risk of overcompaction. When we increase the compaction pressure used to make a tablet, we tend to think of it increasing the strength of the tablet. But there's actually 3 different types of behavior that we see when we increase the compaction pressure. You can see these type 1, 2, and 3. If you look at type 3 in the grey, this is a very common type of behavior where you increase tablet strength and you get an increase in compaction pressure, but only up to a certain point. After that point, the tablet strength plateaus, and the more you increase the compaction pressure, it makes no difference. I tend to think of this as a low risk type of behavior, but if you have, say, APIs that are pressure sensitive, then it can be very important to find out where the optimized point of compaction pressure is for that particular formulation, because increasing the pressure past that point, you're simply wasting energy, and if you have pressure sensitive APIs, you could be damaging your APIs. Type 1 is the ideal behavior, and this is usually only really seen with MCC, where you get an increase in compaction pressure. It's linear initially, but then at a certain point it starts to, the increase in strength you're getting with an increase in compaction pressure is getting less and less, but it is still going up. Type 2 is the risky behavior, and this is overcompaction. You can see that initially, as we increase compaction pressure, tablet strength increases, but at a certain point we hit an inflection point and now the tablet strength is dropping. What's happening here is you're now hitting the tablet too hard and you're creating flaws in the tablet, and this is weakening the tablet. And this is something we want to avoid, or at least be aware of if this is the type of material you're working with in production, because in production, if the decision is made to increase the pressure that's being used to make the tablets, you could actually push the behavior over this edge, so you're ending up with tablets that are even weaker, even though you're using a higher compaction pressure. And I think that's something that's really key to know about your material going into production. That is the final slide from the webinar. Thank you very much for listening, and please get in contact if you want to learn anything more about Gamlen or our instruments.